example 4 from 4.6, we have a trigonometric function. If we do trigonometric functions, I will give you an interval. Otherwise, they just go on forever and ever and ever, and that's just mean-spirited, so I'm not going to do that to you. But we'll go with an interval on trig functions. If you have a homework problem that's a trig function doesn't have an interval, tell me about it and I'll give you the interval. I think they all have intervals though, so. But again, if they don't, just check over real quick after I'm done. And if there's no intervals, I'll tell you what we should have for intervals. So y equals 1/2 x minus sine of x. We're going from x equals -6 to 6. That immediately gets us 2 critical numbers for the rest of our problem. We're only considering these numbers from -6 to 6. I prefer interval notation to compound inequality myself, so I'm going to go that route. It does say equals both of those, so there's brackets on each of those. The technique is the same as it has been. We have our function, that's what we're graphing. Our first derivative is going to tell us stuff about increasing, decreasing intervals and maximums and minimums. Our second derivative will tell us about concavity and inflection points. And it's our job to find all that stuff. So if I go y prime, the derivative of 1/2 x is just 1/2. The derivative of minus sine of x is going to be minus cosine of x. And if the first derivative is 1/2 minus cosine of x, the critical numbers occur at endpoints, which would be -6 and 6. Anywhere the derivative is undefined, which there aren't any, right? Cosine's never undefined. And any place where the derivative equals 0. So basically what I have to do to find out the rest of the critical numbers is set that equal to 0 and solve. I'm going to move the cosine of x over to the right-hand side, so 1/2 equals cosine of x, which means x is equal to anywhere cosine equals 1/2, which would be pi over 3 and 4 pi over, no, let's see, 5 pi over 3. Those are the numbers between 0 and 2 pi, right? 2 pi is 6.28, which is slightly less than 6. I might test 5 pi over 3 just to make sure. Maybe. Here we go. 5 pi over 3. Is it not working? 5. There we go. Pi over 3. Alright, that's less than 6, right?
Yep.
Alright, those are positive numbers, so we also need to go all the way back to -6. What do you think we need to do about that? What am I allowed to add and subtract at will when I'm dealing with radian measure of angles and I want to find coterminal angles? Anybody recall?
2 pi n? 2 pi n?
2 pi is the magic number. We can add 2 pi or subtract 2 pi anytime we want to, right? So 5 pi over 3 and pi over 3 represent 2 places where the cosine equals 1/2. If I take 5 pi over 3 and subtract 2 pi from it, that's 2 pi in disguise, 6 pi over 3, common denominator purposes. I get negative pi over 3. If I take pi over 3 and subtract 6 pi over 3, I get negative 5 pi over 3. Okay, so both of those numbers work too, right? So negative pi over 3, negative 5 pi over 3. I want to test any of those numbers out just to verify cosine is supposed to equal 1/2, right? So if I try, I want to make sure I'm in radians mode. I try cosine of, let's say, negative pi over 3. It should equal 1/2, and it does. Alright, so that just cosine of negative 5 pi over 3.
Will it always be opposite?
No.
Okay.
Cosine, I think opposite sine wouldn't be.
Okay.
So, yeah, it depends on what you're dealing with. But, there you go. So, we've got all those critical numbers. In addition, we have, of course, negative and positive 6. So we have a whole bunch of critical numbers for the first derivative. So once I got my critical numbers, now I need to set up my intervals, smallest number to biggest number, one at a time, right? For me personally, again, I'm graphing this. I've got pi numbers there. I would probably get decimal approximation for each of those. So let's see, pi over 3 is 1.05, 5 pi over 3 is 5.24. So looking at my critical numbers in order, -6, -5.24, -1.05, +1.05, +5.24, and +6. All right. There's all my critical numbers. in numerical order. Again, as decimals, we're graphing things, we're going to be ballparking it. We're pi over 3 and 1.05. I prefer to graph 1.05. I mean, just so if I set up my intervals, starting -6 bracket to -5.24, everything else is parentheses until we get to the 6. There's all my intervals of increase and or decrease. Don't know what they are yet because we haven't tested them yet. And if I do test them, the numbers I'm going to pick are going to be, for this, let's go with -5.5. Let's go with -2. 0 would be fine there, 2 is fine there, and 5.5 would be good here. And what I'm testing is the derivative, and the derivative's function is 1/2 minus cosine of x. So if I type in 1/2 minus cosine of x, go to my graph, my table, and just type in my numbers, -5.5, -2, 0, 2, 5.5. My calculator's not working well. Negative, positive, negative, positive, negative. Negative, positive, negative, positive, negative. Notice that there are no undefineds there, right? Everything's defined, so every one of those changes in increase or decrease is going to leave us with a minimum or maximum of those points. So decrease to increase is a minimum, increase to decrease is a maximum, decrease to increase is a minimum, increase to decrease is a maximum, and also we're decreasing to the end, which we actually are going to hit a minimum at 6, and we're starting with a decrease at the start, so we're actually starting at a maximum, officially. Also endpoints, but if you want to be really official about it, if you have an endpoint, it's going to be the highest or lowest point in this area, right? So you're going to stop there, unless we're going on a flat, which that's not going to happen in the algorithm. So that gives us everything we need to know about the first derivative. So it gives us a lot of information. I'm going to just circle all this stuff. And actually, we should write probably decrease, increase, decrease, increase, decrease. So again, if we're establishing everything, so just looking at this, it goes down, then it goes up, then it goes down, then it goes up, then it goes down. Maybe it looks like that. All right, it doesn't, but maybe it does. But the point is, we know it hits a high, starts at a high point, goes low, then high, then low, then high, then low. We know that much. All right. Concavity is going to give us more information, and again, an XY chart is going to give us specific locations. Something that came up yesterday, there were minimums higher than maximums and stuff on a rational function. With rational functions, you have each asymptote. So this part's going to be part of the graph, this part's going to be part of the graph, and maybe the graph hits a low point over here, jumps an asymptote, and all of a sudden it hits a high point here. That can happen. So don't judge maximums, minimums based on their positions in relation to each other. All right. Anytime there's a break in the graph, it can jump around a little bit. All right. Moving on to the second derivative, I'm going to go into a new page because I'm running out of room here. So let's do that. We know that y prime was 1/2 minus cosine of x. So y double prime is just going to be sine of x. Again, if we're trying to establish critical numbers for sine of x equals 0, sine of x is undefined, never happens, and endpoints will be -6 and +6, right? So where does sine of x equal 0? It equals 0 at 0, again at pi, again at 2 pi. 2 pi is 6.28, so that's too big, so I'm going to throw it out. All right, going back the other way, negative pi. And that's the one scenario where it's the opposite sign. Usually for sine it's not the opposite sign, but remember Chris asked me a moment ago and I said it doesn't happen with sine, it just happens with sine. But yes, coincidental. Just for pi, it'll do that, but other than that, it won't do that. So 0 pi, negative pi, and again we have 6 and -6. And again, I like decimals rather than pi's, so that's 3.14, -3.14. a couple decimal places is sufficient. So if I'm setting up intervals for this, I'm going to go from -6 to -3.14, -3.14 up to 0, 0 to 3.14, and 3.14 up to 6. Again, I'm picking test points on each of those intervals, so I'm going to go, let's go -4 here, let's go 2 here, 2 there, and 4 there will be fine. All we're doing is evaluating sine of x. Good thing I know what sine of x is. Okay, so sine of -4 would put me in the third quadrant, which would be negative. Sine of 2 puts me in the second quadrant, which is positive.
-2.
What?
Should be -2.
Oh, thank you, negative 2. Negative 2 is in the, hold on, did I do that wrong? Try again. Sine of -4, so -4 is in the, going this way, the second quadrant makes it positive. -2 is in the third quadrant, which makes it negative. 2 is in the second quadrant positive, and 4 is in the third quadrant negative. All right. Okay, so just evaluating sine above the x-axis, positive, below negative. So there you go. Positive, negative, positive, negative. So it's concave up, concave down, concave up, concave down. Concavity switches here, here, and here. So that gets us inflection points at -3.140, positive 3.14. So we got a whole bunch of information now. We got a whole bunch of points, maximums, minimums, inflection points. We may have enough information where we can just graph it. That'd be great. A little concerned about my calculator here not working. Smart thing to do here would just be to close it. Let me. Use this calculator. It's much more trustworthy. It's not going to let me down.
Sounds like they're all.
So, let's put all our information down. So I'm going to go 2 pages here and make an XY chart over here. So my critical numbers we got were -6, -5.24, -1.05, positive 1.05, positive 5.24, and positive 6. And then for the second derivative it was 6 and -6 again. We had negative pi and positive pi and 0. -6 was a maximum and an endpoint. And then we had a minimum, maximum, minimum, maximum, minimum, endpoint. And these were all inflection points. So if I get my answers here, the equation I'm putting in, of course, is the original graph. So when I want to fill out an x, y chart and I want to find y values, I need to go back for y equals or f of x equals. So I'm going to go with 1/2 x minus sine of x. And again, I made sure my calculator is set to radians mode because that's the problem, is radians. And I type in my numbers. -6, -5.24, -1.05, positive 1.05, 5.24, 6, -3.14, 0, and 3.1. Right. My outcomes are -3.28, -3.48, positive 3.42, or 0.34, sorry, 0.34. -0.34, 3.48, and 3.28. Little sort of symmetry going on there, it looks like. -3.14, we get -1.57, 0 is 0, and 3.14 is 1.57. So I just got a whole bunch of points. The values range from -3.5-ish to positive 3.5-ish, so not ridiculously large. I could probably even handle maybe a half scale on the y-axis, maybe one scale on the x-axis would be sufficient. So if I get some graph paper out and do that, maybe, as long as this works, let's see. Here's my x-axis, here's my y-axis. Alright, so I'm going to put the x-axis at a 1 scale, with the y-axis at a half scale. 0.51, 0.52, 0.53, 0.5, yeah, that looks reasonable. Fit that on there easily. So, -6, 1, 2, 3, 4, 5, 6, -3.28, 0.51, 0.52, 0.53, 0.5 would be there, so 0.28 would be just a little bit beyond halfway there. It's an endpoint, it's an equals to endpoint, so I put a closed circle. If it just said, if that was just less than, I'd be putting open circles there. Keep that in mind. -5.24, so 1, 2, 3, 4, 5 and a quarter, and the -3.48, which would be almost -3.5, would be just like kind of resting on the line, but not exactly on it. -1.05, positive 0.34, so 0.5 is there, 0.34 would be about 2/3 of the way up. About like that. Positive 1.05, negative 0.34, same deal other side. And then we have 5.24, 1, 2, 3, 4, 5 and a quarter, 3.48, 0.51, 0.52, 0.53, 0.5, 3.48 would be about here. And then finally 6, 3.28 would probably be about here. That's our endpoint. And -3.14, 1, 2, 3.14, -1.57, 0.51, 1.57, probably about here. And positive 3.14, 1, 2, 3.14, 0.51, 1.57, probably about right here. Now those are my points. Right now it looks like one of those data problems from Algebra 2 where we kind of had to estimate the line, right? Kind of scattered, trends going this way, but we can't really tell. If that's enough of a picture for me to establish everything, great. Okay? If I identify things for what they are, this is an inflection point. Oh, I forgot 0, 0. 0, 0 is an inflection point. 3.14, 1.57 is an inflection point. This is a minimum. This was a maximum. This was a maximum. This was a minimum. This was a maximum. And this was a minimum. All right. So it's going to go concave up to this inflection point, concave down to that one, concave up, concave down. Again, I can kind of get a feel for what it's supposed to look like, but this is something that quite a few of you have been asking me about these last several days of these. I'm not sure what the graph's supposed to look like. What should I do? The correct answer is get more points. If you don't know what the graph looks like, get more points. I mean, this is just the ones calculus found us. I didn't pick anything like from 3.14 to 5 point whatever. There's a -4 and a -5 between there, integers that are easy enough to evaluate. I can get extra points. So if I go back to my calculator and pick some integers, -5, -4. -5 is -3.46. -4 is -2.76. So if I plot those, 1, 2, 3, 4, 5, and 3.46. So 0.51, 0.52, 0.53, 0.5, 0.46 be just a smidge above that. All right, and then 1, 2, 3, 4, 0.51, 0.52, 0.5, 2.76 be about right there. There's 2 more points I just found. And now I've got a little bit more clarity as far as what that's going to look like. So again, you can find as many points as you want. You get as many points as it takes for you to feel comfortable about connecting the dots. Just know that there's only this max, this min, this max, this min, this max, that min, these 3 inflection points. Those are the only important points that have to be on there. Every other point is just up to you to get a better picture of what the graph's supposed to be like. I go from inflection point to inflection point. So concave up to that inflection point. That wasn't very good. Try it again. Okay, and then it's concave down to that inflection point, concave up to the next inflection point, and concave down to the final inflection point. I make the concavity fit, and I hit the maximums and minimums. So if it's concave down, I make sure it's concave down, I make sure it hits the maximum, okay? Concave up, I make sure it's concave up and I hit the minimum, all right, and that kind of thing. And that gets me the graph that's supposed to be there. But again, I've been doing this longer than you, so maybe I don't need to have as many points to get a vision of what it's supposed to look like. All right, and again, look at my initial idea. Concave up, concave down, concave up, concave down. I didn't account for the fact that it was rising as it went. And the 1/2 x is what made that happen. 1/2 x is a linear equation. Sine of x is a curvy equation. So you got your 1/2 x line, and the sine is creating these hills and valleys within that 1/2 x line.